Greetings. So, today we will discuss steady state magnetism. Steady means, what do you mean by steady? Independent of time. Okay? Time variant phenomena will not be addressed in this part. But time dependent phenomena of course have to be addressed. They depend on various things, we will get to that. And this part has been developed again by several brilliant experimentalists, some of whom you see on this slide and some of whom you do not. There are several contributors, these are some of the major ones. And we will talk about the important contributions of Biot and Savart. Now, I have no idea how these names should be pronounced. There is a software available on Google and it tells you how to pronounce European names, and I tried it, but I do not think I could pick up the correct way of pronouncing it. So, please pardon me if and when I do not. So, let us consider a charge in motion, and this is the reason I like to call this topic as steady state magnetism rather than magnetostatics. Some people even call it as magnetostatics. In some sense that term is appropriate, but it can also be confusing. So, I prefer not to use the term magnetostatics, because when you have a current, we are talking about magnetic fields generated by electric currents, and electric currents require a charge in motion. So, there is an intrinsic motion that you cannot dispense with when you talk about even steady state magnetic fields. So, I prefer to use the term steady state magnetism to magnetostatics, because the charges are certainly not static, they are not at rest. The charges are in motion and they constitute a current, and sometimes since a current certainly has a direction in which it flows, it is sometimes even, current is sometimes even referred to as a vector, because it certainly has a magnitude and it has a direction. Now, I do not prefer this. So, if you see this equation on the top right, in which I write current as a vector with an arrow on top and write it as a product of a magnitude and a unit vector, I have put a question mark over there, and that is deliberate. So, current is essentially a charge in motion. So, if you have just a linear charge, all right, and you have got a charge per unit length which is in motion at a certain velocity, which is dl by dt, and the velocity has a direction. So, the direction is that of the moving charges which are moving, and then the charge itself that is moving at a certain velocity, which is dl by dt times the unit vector, and this charge is the current, the charge density times the length segment, in that is the total amount of charge in a particular length segment, and the current is then dq by dt, delta q is lambda delta L, and delta L by delta t is what picks up the velocity, that is what constitutes the velocity of the motion. So, this is fine, so far so good. And then you can write, using the direction of the velocity, lambda times v velocity vector as lambda v times the direction of the velocity, the unit vector, and this is fine. But then writing current as a vector is not good, because yes, it has a magnitude and it has a direction, but it is not a vector, because what is a vector is determined not just by these properties of magnitude and direction, but also on how its components transform when you rotate the reference frame, right. There is a cosine law, and then the vectors add according to the triangle law of addition or the parallelogram law of addition of vectors, and currents certainly do not add according to those laws. Okay. So, current adds up according to the Kirchhoff's laws, and this has absolutely nothing to do with the triangle law of addition of vectors. So, here you have got a conservation of charge which determines how the currents flow at a node, and that is how currents are added and not according to the triangle law of addition of vectors, which is why it is not appropriate to refer to current as a vector. So, we are going to talk about steady state magnetic fields generated by currents which are in a steady state, which means that they are independent of time, all right. And you may consider currents flowing in linear charges, but also in surface charges. So, you may have a charge distribution on a sheet which is not necessarily flat, it may have some some bumps and so on. It may have some hills and valleys, but this is a surface, okay, and a surface requires these 2 degrees of freedom which you should specify, and the current is moving in a certain direction which is shown by this arrow, by these black arrows, and the direction which is parallel to these black arrows at any given point is what I will call as the displacement delta L along the parallel direction. So, parallel is parallel to the flow of the charges, okay, and perpendicular, there is another subscript which is used over here which shows a perpendicular subscript. So, this is the direction which is orthogonal to the direction of motion of the charges. So, there is this orthogonal direction and a parallel direction, and you can consider a surface element made up of this delta L parallel and delta L perpendicular. So, this is a tiny surface element. In the limit you can take each dimension to go to 0 and the surface element itself going to 0 to get properties at a given point on the sheet on which the charges are flowing. So, the current which is delta Q by delta T, you can write it as delta Q by delta S and delta S by delta T. So, you are dividing and multiplying by the tiny surface element, and then delta L parallel by delta T is the velocity, it is the speed of the charge, right, and delta Q by delta S is nothing but the surface charge density. So, that gives you current as sigma V delta L perpendicular, all right. So, keep track of the subscripts parallel and perpendicular. So, this is delta L perpendicular, and if you divide this by delta L perpendicular both sides, okay, the left side and the right hand side by the delta L perpendicular, then you get sigma V, which gives you the current per unit transverse length. The denominator is not the length along which the charge is flowing, but it is the length which is orthogonal to that, which is why this is called as current per unit transverse length. And then you can talk about the surface current density, which is sigma times the velocity vector. Okay. So, this is the surface current density, which is current per unit transverse length. So, now you understand what is meant by transverse length. So, you can see that the total current itself, which is the flow of free charges, will be given by the component of the surface current density along a direction which is orthogonal to the unit normal to the surface at that point, and also to the length along which the charges are flowing. Okay? So, it will be given by this kf dot n cross L, and you can always interchange the dot and the cross, and you can write it any which way. All right? You can also have a volume current. So, you have charges moving in a body, okay, and this will give you the volume element to be given by a product of 3 infinitesimal lengths which are orthogonal to each other, and these, one of which is in the direction of the current. So, that is the delta L parallel, and the other two are orthogonal to it. So, you see these orthogonal directions. So, the current is along this black line, and delta L perpendicular is one direction which is orthogonal to this, and delta L perpendicular which is another direction which is also orthogonal to delta L parallel. So, there are two orthogonal directions, delta L perpendicular and delta L perpendicular 2. So, I have indicated these two by superscripts 1 and 2, okay. And then you have got a certain volume charge. So, if rho is the volume charge density, then it is this volume charge density which is moving in that body, and the cross sectional area which is orthogonal to the direction of motion of the charges is the product of the two perpendicular tiny displacements. Okay? So, those are the two tiny infinitesimal displacements, and the elemental current is delta q by delta t, which is delta q by delta v and delta v by delta t. So, delta v I write as a product of these 3 infinitesimal displacements, and now I can factor out this delta L 1 and delta L 2, both of which are perpendicular and one which is parallel. So, the one that is parallel will give you the speed of the charges. Okay? So, if you now divide both sides by delta L 1 and delta L 2, which is the cross sectional area which is orthogonal to the direction of motion, then di by ds perpendicular will give you rho v, and you can tag a unit vector to that, so that you pick up the velocity vector itself, and you get the current density per unit transverse area. Okay, so, this is the current density, current per unit transverse. Transverse means it is perpendicular to the direction which the charges are moving. So, now let us consider that there is a current going in a straight wire, all right, and the current is I, and let us imagine that this current, this straight wire is really very long, and it was known from experiments that it generates a magnetic field around it. How do you know that? If you keep tiny magnets around it, the magnets will get aligned in a particular direction. Okay? It is very regular. So, you keep tiny magnets, just sprinkle them around this wire, and they will organize themselves so that they always point in a particular direction along these circular paths. So, obviously, this is happening because the current is generating magnetic field. If you switch off the current, this does not happen. So, the current is responsible for the magnetic field, and this is something which was known from various experiments people did. It was also known from these measurements that the strength of the magnetic field, and you can estimate that, becomes weak as you go farther away from the current. So, the current is along this wire, and if you go farther and farther away from the current, from the axis, all right, then the current becomes weaker and weaker. And at what rate does it become weak? It becomes weak as the inverse distance. So, this is something which was known, and this is this phenomenon has been known in electric charges as well. You know the Coulomb's law, all right. And if you have charges which are distributed along a straight line, then they all generate an electric field at a certain point. You know that the electric field goes as 1 over r square from Coulomb's law, but then when you integrate over all the line, then the net intensity over there diminishes as the inverse distance. So, you have got the same kind of situation, that the intensity of the magnetic field seems to be diminishing by distance, which suggests that the intensity of the magnetic field must go by as 1 over r square for each tiny element. So, if you consider the current in a tiny element over here, delta L. So, here is a tiny element of the current, and it generates a magnetic field at a field point, all right. So, this is the source point, that is the field point. So, this must diminish as 1 over r square, because its integral will give you 1 over r. So, that relationship is known from mathematics. It is also known from our experience with the electric intensities generated by linear charge distributions. So, you expect that the contribution to the magnetic field by this current element in delta L will go as 1 over r square. It will of course be proportional to the current, because if you increase or decrease the current, it changes accordingly linearly with that. It also depends on the size of the segment that you are talking about. So, it will have proportionality with respect to delta L itself, and dl cross a unit vector in that will give you the correct direction of the magnetic field, which was sort of known from this right hand thumb rule. I believe Fleming's, is it? I think it is called as Fleming's right hand thumb rule. So, if you hold the current in your right hand and point your thumb in the direction of the current, then the fingers of your right hand give you the sense, the direction in which the magnetic field orients itself. So, this was known from empirical laws. So, these are empirical laws, which is why this is actually called as a thumb rule, all right. So, this is the thumb rule. It is not coming from any fundamental theoretical model, but it is coming from your experience from experiments that you do with currents and magnets. So, now you can construct a formal relationship based on this, knowing that the integral of this gives you the 1 over distance, right. And this law would be the same relationship. It is only the proportionality which has now been plugged in, that the magnetic field at a given point, at a field point R2, will be then given by the proportionality which involves the magnetic permeability of free space divided by 4 pi, and then it is proportional to the current in the source, which is I1, and then you have this dl over distance square, and the R2 minus R1 over the cube of the modulus gives you the 1 over distance square relationship, and you pick up the correct direction according to this, right. So, this is what is called as the Biosavart law, all right. This dB equal to this equation that you see at the bottom of the slide is what is called as the Biosavart law, all right. Now, if you now use the Biosavart law and estimate what will be the magnetic induction field, this is called as the magnetic induction field. The B that we are talking about is often called just as the magnetic field, but more comprehensively it is called as the magnetic induction field, because there is another magnetic field which we will be talking about later on when we talk about specific materials which have got intrinsic magnetism, even when there is no current flowing through it. So, we save the term magnetic field for a term that we will need later on, and in anticipation of that, we call this magnetic field B as the magnetic induction field, and this is a magnetic induction field at a distance s from a long straight wire carrying a steady state current. So, the only thing I have done in this picture is I have turned this wire through 90 degrees because it helped me organize this slide a little better, all right. And the net magnetic field due to the entire wire now will be an integral of the contributions from each segment delta L. So, it is this integration that we have to carry out. You can write it in terms of a unit vector, capital R, uppercase R. The caret on top of it means that it is a unit vector. So, it is the difference vector, difference between the field point and the source point. R2 is the field point, R1 is the source point, all right, divided by the modulus or the length of that vector. So, you can write the magnetic field in terms of this uppercase R vector, and it generates a magnetic field at the field point P, which for the segment dl prime, which is shown by this black arrow over here, will be in a direction pointing toward us, perpendicular to the plane of the figure. And you can get it from the Fleming's right hand rule, but here I want you to get it from the Biot-Savart law, because the Biot-Savart law has got a cross product, and that cross product gives you the direction correctly. Okay? So, we will now be referencing to the Biot-Savart law as a fundamental law and dispense with these thumb rules, so that we can really develop a model for magnetism. So, you get the correct direction, and now rest of it is a matter of simple geometry and integration. Okay, because all you have to do is to integrate from left to right depending on the length of the wire, and you can take some ideal case or some imaginary case, if you like, in which the wire has got an infinite length. So, it goes all the way, oops, it goes from all the way to the left and go to all the way to the right, and then integrate over the whole length. So, basic Pythagoras geometry gives you these relationships between the distance and the angle which that current segment, tiny length segment, subtends at the point P, right, with respect to some central point. And then using this geometry, which is nothing but the Pythagoras theorem, you now have to integrate from theta 1 to theta 2, where those are the angles subtended at the end points. Okay? But if these end points go to infinity, okay, then it will, this line, this oblique line will become more and more parallel to the current itself, to the current wire itself, and eventually it will pick up the values minus pi by 2 and plus pi by 2, and you can see that the magnetic field will go as inverse distance. This is exactly what we began with, because that was the finding of experiments, and this is what Ampere's law is about. So, Ampere's law tells you that the magnetic field at a field point of an infinite straight wire is proportional to the value of the current and inversely proportional to the distance from the straight wire itself. Okay? And that the direction of this field is given by the Fleming's right hand thumb rule. So, this is now formally constituted, and we see that it comes from an integration of the Biot-Savart law, which has got a look very similar to the Coulomb's law, because it also has the inverse square in that. So, it has got a similar structure, and so the reason it has got an 1 over r square structure is not so much because you are constructing it as a parallel to this, but because you know from the Ampere's law that as you go farther and farther away, then the magnitude of the field decreases as 1 over distance. And if you are to get that from integration of contributions from different elements, then each contribution itself should go as 1 over distance square, so that its integral will give you 1 over distance. We know that the differential of 1 over distance is 1 over distance square, and the integral is the inverse, right. So, here if you integrate B dot dl over a closed path, okay, then it becomes independent of distance. And the reason is that the path length itself, which is the circumference, it increases linearly with distance, and the magnetic field itself diminishes linearly with distance. So, those two effects compensate and cancel each other, so that the integral of B dot dl becomes independent of distance itself. So, this is the Ampere's law. And now if you have two currents in two independent wires, so I1 and I2 are two currents. And now what have we learned? That the current in I1 generates a magnetic field, and it is generating a magnetic field at the point P2 through which the current I2 passes, which means that there is some charge at the point P2, because it is the charge in motion which constitutes a current. So, there is a charge element at point P2, and now this charge is not static, but it is in motion, because it is part of the current I2. So, you have got a charge in motion in a region where there is a magnetic field which is generated by the current in I1. The current in I1 we know from Biosavart law and Ampere's law, but more appropriately from the Biosavart law, because Ampere's law is when you apply it to an infinite straight wire. Biosavart law is a fundamental law, and you can apply it to current in any shape. So, you have got a closed current, it can be a circle, it can be twisted, it can be warped, right. But then you have got a current flowing, and this current will generate a magnetic field at the point P2 where you have a charge in motion, and this charge in motion will experience the Lorentz force, because the Lorentz force is Q into V cross B in the region where B magnetic field is present and the charge is moving at the velocity V. And if that is the case, the charge segment or the current segment in the current I2 will experience this charge, but this will happen to every segment in the current I2, and the whole wire in which the current I2 is flowing will experience a force because of the magnetic field generated by the current in I1. And the origin of this force is nothing but the Lorentz force. It is because you have got charges in motion. So, Q into V cross B is what is responsible for this force, and this force you can estimate now using Lorentz force law. So, how do you do that? You just set up a frame of reference. So, you have got a source point R1 and a field point R2, all right. You know the Lorentz force law, which is Q into E plus V cross B. So, you must find the magnetic induction field at the point P2, for which you will use the Biosavart law, all right. Then you must find what is the charge at the point P2, that you get from the current, because if you know the current, you know what is delta Q by delta T. So, current times delta T will be the charge element over there, and that charge element will experience the Lorentz force, and then you just integrate over the whole loop. Okay. So, the technique is very simple. So, let us apply it now. So, you have got a unit vector at the point R1, at the source point R1. This unit vector will change its direction from point to point on the current loop, all right. And the force it will exert on a charge element delta Q at the field point R2 will be given by the Lorentz force law, which is delta Q into V cross B, but then you multiply and divide by delta T and pick up the current from delta Q by delta T in the first step, all right. And from V delta T you get the current length segment. It is velocity into time, which is distance, and this is the distance through which the charge moves in the direction of a unit vector u at the field point, which is UR2. U, it is a unit vector, so it has got that caret or cap, all right. So, this is the V delta t, and now you have to find what is the magnetic field at the point R2. Now, this is given by the Biot-Savart law. So, from the Biot-Savart law, you know what is the field generated by a length segment delta L1 in the source current, which is current I1, and you need to integrate this over the entire loop of the current in the wire 1, which is current I1. So, this is integration over the closed loop. This is nothing but the integral of the Biot-Savart law. Alright, so we have come this far, and now we can put this magnetic field in the expression for the Lorentz force to determine the net force on the charge element in the current charge element in the wire 2, in the second wire. So, that is given by this first expression over here. So, you have got I2 UR2 delta L2, which is this, and BR2 is given by this Biot-Savart law. So, now you have everything that you need, right, and the net force on the entire loop 2, not just on the current segment at the point 2. Now, you need to integrate over the second wire. So, the integral over loop 2 is what you need to carry out, and now you have two full integrations over closed loops, one over the wire 1 and the other over the wire 2, to get the net force exerted by the wire 1 on the wire 2. Okay? So, this is your final result, in which you of course have the magnetic permeability of free space, which has got this particular value in the SI system of units. So, you can now use this for line currents, but we have already discussed that you may also have surface currents, in which the Biot-Savart law takes it requires a double integration, because you have one more dimension which is added, and you may also have a volume current in which you have got a triple integration involving the corresponding current density vectors. So, you have got the surface current density vector or the volume current density vector, but then these are the currents flowing orthogonal to the surface, and this is the volume current which is flowing in a direction which is orthogonal to the cross section, right. So, these orientations I have discussed in the first part of today's class. So, you have the line current, the surface current and the volume currents. So, you have got now this Ampere's law, which is written like this, B dot dl, right. And what does it mean? Integral over a closed path, we know from vector calculus, if for any vector field which has got well defined derivatives and so on, all right. So, it has to be a well behaved function, it has to be analytical. So, given assuming that those conditions are satisfied, then the line integral over a closed path is completely equivalent to a surface integral. Okay. The current itself is the surface integration of the current density vector. So, J dot ds over the open surface, which is orthogonal to the direction in which the current is flowing, right. So, that will give you the net current. And if you now equate these two, you see that you have two surface integrals which are essentially over exactly the same surface elements. These are definite integrals, which means that the corresponding integrands must be necessarily equal, which tells you that mu 0 j must be equal to the curl of B. The physics in this is no different from the physics in the Ampere's law. So, this is also called as the Ampere's law. This is the Ampere's law in differential form. What you see in the first equation at the top is the Ampere's law in the integral form, right. And essentially what it means is that the magnetic field is such a vector whose curl is non-zero. If it were 0, you would call it as an irrotational vector. Irrotational vectors are those for which the curl vanishes. In this case, the curl does not vanish, and you call it as a rotational field. But we obtained this using Ampere's law for an infinite straight wire. That del cross B is equal to mu 0 j is valid not only for an infinite straight wire, but if you have a current flowing in some arbitrary loop, all right, and now you cannot do the integration the same way as you did in the previous exercise. Even then, whatever magnetic field this current generates is still irrotational. It is still rotational, I am sorry, okay. It has a non-zero curl, and it is given by exactly the same relation. Now, this is not something which we could have anticipated, because in the Ampere's law we got it under rather comfortable circumstances in which we could carry out straightforward integration from minus infinity to plus infinity over the straight path, so that the two angles theta 1 and theta 2 become pi by 2, right. Or so this is an amazing result that it holds good not just for a straight wire, but for anything and everything. And if it is to hold for a current in any shape, not just a straight wire, then we have to be able to get it from the integration of the Biosavart law for different loops, right. So, the Biosavart law becomes much more fundamental in that sense of the term. So, this is the Ampere's law in integral and differential forms for infinite straight wires, and using this to other circuit elements, we can use the Biosavart law to other circuit elements. You can have current in a circular path in a flat plane. Now, I have chosen somewhat. Now, this is no longer an infinite straight wire, so it is not the same geometry as earlier, but it is still a simple geometry, okay. So, we will introduce more and more complexity. So, we will use the simple geometry first, that you have got a circular path, it still is regular, it has got a specific geometrical shape in which the current flows, and the field point at the magnetic induction field at the field point R2 is given by the integration of the Biosavart law, right. And you can see that the horizontal components of the field will cancel because of symmetry, right, and it is the vertical components which will add up. So, the vertical components are the components along the z axis. So, the component along the z adds up, in this case the addition is nothing but the integration, right. So, you integrate over the closed path, and the closed integral of dl, the length segment over the closed path on the circle, will give you twice pi times the radius, which in this case is considered to be little a, and you can see from this very simple geometry that you have an expression for the magnetic field at this point, all right. So, you can write it using the Pythagoras theorem in terms of the radius of the circle and the distance from the center of the circle above the plane of the circle, okay. So, you can write it in terms of a and z in this figure. So, I put an asterisk over here on this equation because I will refer to this equation again very soon, because I will use it to determine the magnetic field of a solenoid. Now, a solenoid can be thought of as many of these circles packed together, okay, and we already have the result in the equation which I refer to with the asterisk. It gives you the magnetic field due to current in a circular path, and you have so many of them in a solenoid, so you can just add them up. You can take that result straight away and pack it and add it up. So, This is a densely packed solenoid, so that the total number of turns is capital N. If the total length is uppercase L, then you have the number of turns per unit length to be capital N by capital L, right? And now you can determine the magnetic field at a point inside the solenoid. So, let us determine it at a point P on the axis. Okay? And you can locate this point in terms of a distance from one end, which is ZP, and distance of an arbitrary segment of the solenoid is referenced from the same end in terms of Z prime, okay? And this difference Z is Zp minus Z prime. So, that is the geometry we are referring to. So, we can determine the effect at P due to a small segment dz prime, which is located at Z prime from one end, and then integrate from left to right, covering the entire length. So, that will be our strategy. So, the number of circular rings in the small segment Zp, we can get it because now we know the number of turns per unit length. So, we know the density of those circular coils, and you use the result, which is that asterisk result which I referred to earlier, and you just take that result, pack it and add it up, okay, because the number density is known in that segment dz. Okay. So, now you have that, because there is not just a single coil in this element dz, but n times dz, n times dz prime. Okay. So, now you have to integrate it, but you are integrating over z and not over z prime. So, dz prime is minus dz. So, you just keep track of the signs and the Pythagoras theorem and the geometry and integrate from one end to the other, and you get a straightforward integration result. So, you can write it in terms of the cosine of the angle subtended by this, and these angles will become 0 as the length of the solenoid increases, so that their cosines will become 1, and you are adding 1 to another 1, which even in the laws of electrodynamics 1 plus 1 is equal to 2. That cancels the 1 over 2 in the in this expression, and you get the magnetic field of an infinite length, which is B equal to mu 0 n I. Now, what is amazing about this result is that other geometrical terms inside the solenoid do not appear anywhere. It does not demand that it has to be on the axis, it does not demand that it has to be at any particular position, which means that in the entire solenoid, the magnetic field is mu 0 n I, which is constant. It depends only on n and I and does not depend on the actual position inside the solenoid, which is in some sense a strange result. This is not what we could have easily guessed, but this is in some sense really strange, because the actual location of the point becomes completely irrelevant. So, it gives you a very nice homogeneous constant uniform field inside the solenoid. So, if you really want uniform magnetic field, you should use a solenoid. It is a great source to generate homogeneous uniform fields. And the reason it is happening is because you have, in the solenoid you have got the current which is going, which is flowing in every circular coil, in a particular direction. So, here we consider the current to be flowing in such a direction that at the top of the coil it is going into the plane of the figure and at the bottom it is coming out. So, if you now draw this, right, and just consider an Amperian loop over which you determine this line integral, then it is given by mu 0 I. This is the Ampere's law, right. And the current which is enclosed in this loop is the same even if you move the loop up or down, which is why the magnetic field remains invariant even as you move away from the axis. So, the Ampere's law gives you the correct account of this. It describes it. Ampere's law is not the reason that the magnetic field is uniform. The magnetic field is uniform is because of the geometry, because when you are considering infinite lengths, then these small distances here and there are no longer relevant. Okay? So, there is a physical reason for that, but the Ampere's law describes it correctly. So, you have a uniform magnetic field in a solenoid, but then we found that the curl of B is given by the current density vector. Curl of B, we said, is a rotational term. The magnetic induction field is rotational. It has a non-vanishing curl, and what is its value? It is equal to mu 0 times the current density vector, mu 0 j. But we got that result for an infinite straight wire. Is this true for an arbitrary shaped wire? We can check it out. We have the Biot-Savart law that we know is true no matter what is the shape of the current, right? And we can find, given the Biot-Savart law, what is its divergence and what is its curl. So, when you take the divergence, you are going to need the divergence of 1 over distance square, and we discussed this yesterday that the divergence of 1 over distance square is 0 or 4 pi. That depends on whether the point is at the origin or away from the origin, right. So, we learned that it is described by the Dirac delta function, and using this we can now find the divergence of the magnetic field. So, let us do that. It will turn out that the divergence of B always turns out to be 0 given the Biot-Savart law, no matter what is the shape and size of the current element. Okay? And also the curl of B is always mu 0 times j, no matter what is the shape and size of the current element. So, these are universal laws. These are much more powerful than just the Ampere's law, which is of course valid, which is correct, but for an infinite straight wire. All right. So, let us determine the divergence of B. So, you begin with the expression for the Biot-Savart law integrated over the volume current, which is the source current, right. BR2 is the magnetic induction field at the field point R2. You are integrating over the entire source region. So, the integration is over the variable 1, and the differentiation is with respect to the field point. The integration is with respect to the source points. These two are completely independent, right. You can consider different field points without moving the source, and at the same field point you can find what will be the magnetic induction field if you move your source. Okay. So, the differentiation with respect to the field point and the integration with respect to the source are completely independent operations. So, you can move the operator gradient inside the integration and take the divergence of j cross r over r square. Got it? So, now we have to determine this j cross j over divergence of j cross r over r square. So, this is the divergence of a cross product of two vectors for which we can use the vector identity for any two cross product of any two vectors. Cross product of any two vectors, you take A cross B and take its divergence, it is given by this particular expression, and if you now take the divergence of this, you just replace A and B by the terms which are of interest to us. So now you have this result. Okay. Now notice that in the first term you have got the gradient of the current density vector, but the current density vector at the source point. Okay. You are taking the curl, the cross product. Okay. Not really the cross product, it is a curl. Cross product is a term that you would use if you are using two vectors. Gradient is not a vector, it is a vector operator. So you have del cross J, but J is at the source point and the gradient is taking differentiation with respect to field points. So these are independent, and del cross J R prime will go to 0, right, because the current density at the source point has nothing to do with how you change the field point. So the first term goes to 0, now you are left with only the second term, and the second term you have to take the curl of this, right, and you can evaluate this expression and it turns out to be 0, okay, and that essentially means that the divergence of B is always 0, which is a very powerful result. This becomes an integral part of Maxwell's equations, and here we have seen that this holds good not just for a straight infinite straight wire, but for current in any shape, no matter what it is. So divergence of B is always 0, and if you have a vector field whose divergence goes to 0, it is called a solenoidal field. Okay, as you can see in the solenoid itself, you have seen the magnetic field, it is uniform and constant, so whatever flux comes at one end, it remains invariant. So its divergence goes to 0, so it is called as a solenoidal field. And then we also find what is the curl of the magnetic induction field. So you have to take, once again I have moved the operator curl, the gradient operator inside the integration because it is differentiation with respect to the field point, the integration is with respect to the source points. Okay. So now you have the curl of a cross product of two vectors, not the divergence of the cross product of two vectors, but the curl of the cross product of two vectors. So now you have got 4 terms, 2 of which will vanish because one of the terms is a current density vector at the source point, and whenever it is operated by differential operators which are seeking variations with respect to the field point, you will get 0 because they are completely independent. So 2 of these terms vanish. The other 2 terms are what have been written here. So let us analyze these 2 terms, of which one of the terms involves divergence of 1 over distance square, so that we know is given by the Dirac delta times 4 pi. So we have this result, and then you have the other term, and to look at the other term we will use some simple tricks. So one term has already been taken care of where you get the Dirac delta, that is the one which will turn out to be the more important one for us. So you have the Dirac delta in the first term, and then if you will need the volume integration over this region. So when you do the volume integration of a product of 2 functions, one of which is the Dirac delta, you will have the shifting and you will get only one particular value, which is the current density at R. So that is what you will get from the first term. From the second term you have this expression. Now look at this term in this bracket, okay, the J dot del. J dot del is an operator. It operates on an operand, which is this. The operand is a vector. It is the difference vector r minus r prime divided by the cube of the modulus of the difference vector. That is the operand. So, the operand, which is a vector, I can break up into three components, three scalar components, three orthogonal scalar components. So, the first component will be x minus x prime divided by r cube, and then you will have similar terms for y minus y prime and z minus z prime. So, I am looking at a particular component, which is the x component. So, I take this term, which is the second term in the expression for the curl of B. I look at the x component and I use a vector identity for the divergence of a product of two functions, one of which is a scalar and the other is a vector. F is some arbitrary scalar function, A is some arbitrary vector function, and the divergence of the product of f and A is given by this identity. I use this to get the divergence of a product of a scalar function, which is x minus x prime by over r cube, and a vector, which is the current density vector. So, I use this vector identity to express this and I get this result. And I am interested in this result because I am interested in this last term, j dot del x minus x prime over r cube. This is the term which is coming here. So, this last term is the left hand side minus the first term, alright. So, this is the left hand side minus the first term, and I put that back over here, and now I interchange an r and r prime. Now, this is just a clever mathematical trick, because see, it enables us to get our result very easily. You can get it even if you do not do it, but then the argument becomes a little more complex. It is much easier to just swap the notation. Okay, you are not swapping the positions of the source point and the field point, you are only saying that okay, you are now describing the source by r and the field point by r prime, okay, which is just the reverse of what we were doing earlier. So, if you interchange the notation r and r prime, then j with argument r becomes j with argument r prime, and the gradient operator becomes the gradient with respect to the primed variable. Okay, so, this is now the notation. So, it is the same equation as the equation I have written in the red above it, except that I have interchanged the primed and the unprimed notation, but that I do also for the operators. So, when I change the operator del to del prime, what I am doing is instead of taking del by del x, I will be doing del by del x prime. Okay. So, instead of taking the differentiation with respect to x, it will be differentiation with respect to x prime, and these two are completely independent of each other. So, I have changed the notation. The last term involves the divergence of j, and the divergence of j in steady state is 0. That comes from the equation of continuity. We have studied that in fluid mechanics, right. When we discussed fluid mechanics, we found that the divergence of the current density vector, which is given by del rho by del t, okay, and rho was the mass density in fluid, but it could also be the charge density, and I had mentioned this when we discussed the equation for continuity in fluid mechanics. So, it is exactly the same equation for a steady state, since del rho by del t is 0 for a steady state. Steady means things are independent of time. Divergence of j is 0, so the second term vanishes, and now you are left with only the first term. So, let us analyze this residual equation, all right. Notice that you in the operand of the gradient you have got x prime minus x. So, x prime and x have opposite signs. So, there is a sign disparity. So, if I change the differentiation with respect to x prime to x, the corresponding operator will pick up a minus sign. Okay? So, as a result of that, if I replace this operator del prime by del, so instead of the prime I have the unprimed gradient operator, then I have a minus sign here. Okay? Everything else remains the same. So, this is the result that we have. Okay? So, I have only moved the minus sign from the left hand side to the right hand side, and I mark it by this asterisk, which is a result which I will use very shortly. And I have the previous result in which I had this integration involving the Dirac delta, and the second term was this, right. And now in the second term I use for this integrand this particular term with a minus sign, but there is a minus sign here and there is also a minus sign here. So, the two together will give me a plus sign here, and now I have got the integration. Mind you, everything is primed over here. I have got the divergence integral, volume integral of the divergence of a vector. And what is the volume integral of the divergence of a vector? It is a surface integral of that vector over the closed surface which bounds this volume. That is the Gauss's divergence theorem, right. So, using the Gauss's divergence theorem, I write it as a surface integral. And what surface is this? I can choose this surface very far away to include the whole region, and out there is no current density, there is no material current density flowing at infinity. All right, I go far enough, and when I do that, the second term vanishes and I am left with only the first term, which is the same result as we got for a straight wire, and this is for an arbitrary wire. This is amazing, is it not? And it comes from, very simple but rigorous vector calculus. We have used the Gauss's divergence theorem, we have used the equation of continuity, we have used the Dirac delta function integration, and all of this comes together to establish that the magnetic induction field is a rotational field. It has got a non-vanishing curl which is equal to the current density vector J. It will of course be 0 if the current density vector itself is 0. So, it is not that it is always non-zero. It is equal to the current density vector times the permeability of free space, and it will be 0 if the current density itself is 0. Not just for an infinite wire, but for a current flowing in any which way. So, thank you very much. I will be happy to take some questions, and if not, thank you and goodbye.